Hi, everyone. Am I on?
We are on. We are live.
Exciting. Thanks for joining us. So as Joseph mentioned, we're from the Spot.io team. We're both solution architects on the team. And we want to talk to you today about implementing serverless scale Kubernetes in as you all might have seen, there's a Q&A available in the platform in Hopin. So Joseph is there to answer your questions. Feel free to shoot them out throughout the session. And Joey, if you feel like one of them is really relevant to the audience, feel free to interject me and have us respond to that in front of everyone. So once again, thank you all for joining us today. I do want to quickly start by discussing for the anatomy of Kubernetes. You all probably know Kubernetes is probably the leading container orchestration platform out in the market today. Started originally inside Google, calling itself Borg, managing the entire Google data centers. Its component, on one hand, you have the control plane. So this is where your master is, where the etcd, the API server, the Kubernetes scheduler that actually puts your container on this. And on the other side, you have your data plane. Essentially all your worker nodes, where all your applications sit, where everything you're running is working on. This is the majority of your cluster, even though a lot of the cluster configurations sit in the master. You will normally either have a managed control plane, like an EKS, AKS, and others, while you will have normally unmanaged data plane, which is all your worker nodes, can be hundreds and thousands of cluster. You have your node agent in every single node that knows how to kind of manage the node itself. And you have your services coming as single controllers in the applications themselves. What this is causing, because you have all your workers running as pods and running containers inside of them, really two separate layers of scaling. The first one is your containers themselves. So you're using scaling policies that increase the replica count, you increase the number of containers based on specific requests. We'll shortly discuss what are the alternatives to do that. And the struggle many times comes because you have another layer of scaling, which is where you're running your actual infrastructure. As flexible and dynamic as container orchestrators are, and it feels like they're a natural fit for the cloud, which is also extremely flexible and dynamic. Though they weren't built for that. They were built to run data centers. As you mentioned, they started off with Google. And really one of the struggles with that is that there's no native capability for container orchestrators to scale infrastructure efficiently. Set those two different layers separately and making sure that your infrastructure catches up with the request of your containers. And that becomes extremely challenging as your Kubernetes adoption keeps growing in your organization. Today you have 2 apps in containers, and then you'll find yourself in just a year or 2 from now with 100 or 200 apps of containers that are containerized. And each one of them will have its own scaling rules based on what's best for this application. And you're kind of trying to capture all of them with very few scaling capabilities in the underlying infrastructure. And I'm going to discuss during this talk about kind of like the old method and what we see to be the future method and the more efficient way to achieve that. So as promised, we want to talk a bit about the Kubernetes scaling. So your first and most common option is the horizontal pod auto scaling. You're checking a specific metric that is application relevant, that can be the basics like CPU and memory, but maybe things like throughput, number of connections, number of hosts you're using, number of sessions, and things like that. And every time you're meeting that threshold, you increase the number of replicas. So if you would want to think about it in non-containerized environments, you would add another server, but here you're just increasing the replica of the Kubernetes deployment. And then Kubernetes balances the load. That happens every few minutes. You can go over the deployment to 500 replicas in a deployment. And ideally, you would want to in your infrastructure to catch up with that. The other alternative is the vertical pod scaling. So essentially, you take the very same container, and the moment it meets certain thresholds, you redeploy it just bigger with more resources available to it. You're still talking about scaling that same container. That would mean you would have to scale the underlying nodes available for it as well at the same time. So it's a bit trickier. Google allows you to kind of scale flexible node sizes. Amazon offers a gigantic variety of nodes, but you would have to know how to leverage them efficiently. And this really creates a problem. On the one hand, you want to meet your application demands. And really the easy way to do it in the data center is that your application simply has a data center available to it. And what's there is there. And if you have to quadruple in load overnight, you just can't do it. That allows you to do. You can 10x your infrastructure at the push of a button sometimes. However, because of the utility billing, you're paying per second for everything you use. And the real challenge is meeting those demands while minimizing your idle resources and getting the most bang for your buck. It would be really easy to just throw 10,000 nodes on your cluster and making sure you always have uptime and your resources available. But from a business sense, it probably wouldn't make sense to run an application like that and still keep it with decent margins. So we want to solve this problem, meeting the demands in real time and minimizing idle resources at the same time. And we want to do that across 3 different layers. So we want to get instance size, get the right size of machine and the right family at the right time based on our application requirements. We want to do it by the instance lifecycle. We want to use all the reservations, all the commit usages that we have when we have them available, because they're cheaper than using something you've already paid for. After that, we probably want to use cloud access capacity. They're called spot instances in AWS. They're called preemptible VMs in Google, and low priority VMs that actually recently turned into spot instances on Azure as well. And only then we've leveraged those capabilities, we want to move over to on-demand servers. Lastly, and not to be discounted in its importance, size of the containers themselves. So we can beat back the infrastructure as much as we want, but if our applications are making requests that are 10 times louder than what they're actually running, then we're spending 10 times as much on our infrastructure. So we want to make sure that all these things are optimized in real time and stay as efficient as they can. We've seen clusters that are able to, from the sized on-demand cost to properly sized spot cost, can reduce the spend by 90 to 95%, which is extremely significant. And I'm talking here about clusters that would otherwise cost $100 a month. So I'll talk a bit about the challenges that this creates. So essentially, what I'm calling this notion Tetris scaling. So you're scaling like a Tetris game. You're using different shapes of instance sizes and families because, again, you have different applications. That. So let's say we have each one of those small squares here is a unit and a scale up. And this instance is still free. And we have a pod. And that pod comes requesting 3 squares. And essentially, we have 2 units available here, a unit available here, and a unit available here. And we have enough capacity in the cluster, but we don't have the ability to run that container on any one of those given servers. Because of that, even though even might have scaled up with that extra node, and it now has enough capacity to answer that container, it doesn't have the ability to do it by itself, and that pod would stay in a pending state. So we want to make sure that even though we have those 2 units available here, we have to discount them when this pod comes in, and we need something that has 3 units all by itself. Another issue that can happen. So same thing, your pod is stuck in a pending state, you scaled up too small, and you're still stuck in that pending state. Another issue that can happen when you scale down. So saying, hey, there's these 3 access units in here, and there's 3 units in here, that this is what this application is. So I'll drop this server, and I'm not paying for that waste. But this container will get stuck in a pending state again, because it's not able to fit on the access of those servers. That being said, if you had something that was smart enough to know that, it could, in theory, ask this container to drain itself and then hop over to this node. And then this container could land on this node. And you could run that same load. You had 4 different servers, or 2 small ones and one that's 4 times larger than with just the 2 smaller machines. And that you could do if you would be able to intelligently understand the 2 layers of scaling at the same time. And I think there's a different approach to do that, and that there's a better way to achieve those results. And that is really container-driven scaling. So start thinking about nodes and start thinking about infrastructure, rather than about your containers, your applications, and what really runs your business logic. At the end of the day, most businesses out there are not making the revenue because they orchestrate containers efficiently, but rather because they have a great application that inside these containers, which is what they're saying. So keep your focus on what and on how you can bring value, and there's a better way to manage infrastructure while doing that. So we essentially want containers to be first-class citizens. We want the instance, the type, and its price to essentially be determined by the container itself or by the pod, while honoring all the labels, the taints, the tolerations, the networking, and the storage requirements. If you have a small pod pending, you can scale up a T2 medium. If you have a larger one, you can scale up a C5 to extra large, all AWS terms, by the way. If you have, maybe you want to do a C5 extra large right now. And more, let's say your data scientists have analyzed their models and they platform that you offer internally. They're trying to deploy their model, and really what happens is that they fail. There's no instances that match it using computer vision models, let's say, and they need GPUs to be running. So able to answer their request, answer every new greenfield or greenfield development or brownfield refactoring, to really be able to join your platform and your internal containerized platform pretty much instantaneously, without having to answer those Teams calls every time, understanding their needs, set up new groups and new infrastructure to match them. But rather, in this case, you would want them to simply deploy their models inside Kubernetes. Kubernetes see that there are deployments asking for GPUs, and then go look for the cheapest, most highly available GPU instances out there. Let's say in this case, a G2 XL. Now, lastly, just won't be a good fit for anything that runs on low priority support instances. So we would want to make sure that, again, specific application requests to stay in place and never be moved around. That will be a flag on the containers themselves. Again, no new infrastructure. And have your autoscaler node to launch on-demand instances whenever these pods come in, instead of having idle on-demand servers always there. That really Kubernetes plane management. So we have control plane management. Every cloud provider is offering one today. You also have KOps, the open source one, and the OpenShift by Red Hat. You have your Spray and many different distributions that are being built in-house for some companies as well. But there are every new organization kind of figuring out how they want management. It can be a single node pool, it can be multiple node pools, it can be with a cluster autoscaler, without a cluster autoscaler. But really, there's a lot more efficiency when you think about large-scale implementations of dozens of applications and a lot of usage. And really, what does that mean when you have a serverless or nodeless experience? It means you're not managing any underlying infrastructure. You're not managing the servers, but rather the Kubernetes. Scaling by requests based on real-time requirements. You don't have access idle resources. It's, again, the cloud's utility billing. You only want to pay for what you use, and you want to eliminate waste. You only need economics of final application. Because you're running in sort of a serverless experience, you want to be able to scale all the way down to 0, probably not in production, but in depth. Maybe you can shut things off at night and not pay for them. Or just if applications are not running, the cluster should know how to scale itself down and not keep usage for nothing. And lastly, because you're scaling further down without keeping idle resources, you would want to be able to scale up quickly. So fast scaling. Whatever containers coming in, whether that HPA I mentioned goes 5 to 500, maybe it does that all at a single scaling event. And it knows that at 9 a.m., all the connections start, and at 8:55, it goes through that. You would want, again, your autoscaler to see more than 95 containers. I need 100x the resources right now. And within a single request, you would want all of it to be answered. Because step scaling would achieve that for us within only about sometimes even 30 or 45 minutes. Now, obviously, as engineers, we all like numbers. So it's important to understand what we're gaining out of this and what does pod-driven scaling mean. So let's take this example. You have a pod or a container that requires 6 bytes memory and 1 vCPUs. And you put it on an M5, and you use up 81.25% of its memory, and you use up 75% of its CPU, which means pretty much everything left here is useless because you cannot put another container on it. So the unit economics per hour to run that container is 9.6 cents. Now, let's say we go up one. Now, we're going to pay twice as much. We're going to get twice the resources, and we can put twice as many containers on it. So same utilization, same unit economics. We gained nothing here. But let's say we go up another instance size. We get twice the resources. We're paying twice as much. But all of a sudden, we can put 2.5 times as many. Which means we're getting our memory allocation up from 81.25 to 0.44. And as 75 to almost 94. Because of that, we're actually getting a single container to suddenly run for 7 cents an hour instead of 9.6. And we're actually getting about 20% cost discount or cost reduction for these containers. Just a machine that can impact them better. Now, let's take that similar pod and how it gets much worse, really, when you're thinking about different families that aren't being packed efficiently. So a pretty high memory pod, 6.5 gigs of memory to 1.8 vCPUs. Now, the cheapest way to answer a single one of these pods will be a C5 extra large AWS. You use 82% of the instance memory, but only 45% of its CPU. So you're paying the 17 cents an hour that it's costing you for that pod. Now, if you understand that this is a pretty high ratio of almost 1 to 4 between memory and CPU, you'll be able to know that, and if your autoscaler will do it in container-driven way, you'll be able to switch from a high CPU machine to a high memory machine. And then suddenly you're getting the same efficiency on your memory, 81.25%. But you're doubling your efficiency on the CPU because you're using the same machine size, containers on it. Really, the cost difference, because memory is cheaper than CPU, is only about 10%. And because of that, you're reducing your cost per container by about 43%. Now, again, doing these calculations once is nice and easy, but when you have hundreds of applications split into thousands potentially of microservices, nearly impossible for you to do by yourself. And that's why I want to scale requests in real time and not constantly plan for that and hope for the best. And to tackle that exact problem, essentially, we've built Ocean quickly But Ocean by Spot really solves all these 3 different layers of optimizations for you by plugging into any existing Kubernetes cluster that you have. We put a single container in the cluster that allows us to handle all the container-driven auto scaling, handle all the instance requests in real time, all the cordoning and draining of nodes, and all of that happens instantly. We will help you simplify operations by essentially allowing you to deploying more and not managing the underlying infrastructure. Really, again, container-driven auto-scaling, maximizing your resource utilization, the bean packing of everything, understanding network topology to make sure that containers get to sit together, and really maximizing kind of all utilizations. Now, as I mentioned, you can bring your own control plane. Ocean will seamlessly integrate into any existing stack, whether yes, as well, by the way, all types of Kubernetes, EKS, GKE, AKS, COPS, OpenShift, and many others. And by leveraging all your existing reservations and leveraging Spot instances for you and right-sizing your containers, we get you 90% cost optimization there. Additionally, our dashboards will give you cost management and showback, show you granular costs to the container level so you can understand the costs go and of labels and notations, as well as by namespaces. As I mentioned, will help you in real time measure the resource usage of the container, automate of them, either automatically or through the suggestion engine. And of course, all of these will connect with your existing tools stack. We have support for Terraform, Ansible, CloudFormation, SDKs in many languages, and RESTful APIs. This is it for me. Thank you all very much for joining us today. If you have any questions or interest in what we're doing here, and if there's anything you have more curiosity on and you didn't have a chance to ask, please don't hesitate to reach out. Thank you, everyone. Do you have any questions that came up?
No questions came through the chat as of yet. Perhaps no, that was it.
Okay. Thank you, Philip. Thank you, Raj, for joining us. If anyone has anything else, I'll stick around for another minute or two if you ask it on the chat. I'm looking at it right now and more than happy to answer. Have a wonderful rest of your day and enjoy the conference. Someone asked if we need to install anything to it's running. It's a single container, so a single deployment. It takes about a single to simply connects with our platform that knows how to interact with your environments to make sure that all the orchestration happens. Plugging in a cluster and getting it to essentially become serverless for our platform takes about 15 or 20 minutes until you never have to manage your infrastructure on it ever again. So customers, including a Ticketmaster, run all their production environments on top of it. We've done a talk together at reInvent. VMware is using it, and many other enterprise and high growth companies are using our services. Someone asked if the workload has to be full in case the Spot instances get killed or preempted. Yes, generally our platform will be able to run the cordoning and the move over to new nodes. So if you have replications on the deployment, then that normally won't be an issue. We also have awareness to persistent volume claims and any other disruption budgets and any other kind of Kubernetes configuration. Make sure that becomes as seamless as possible. The application has to have some fault tolerance, but again, it's not an all or nothing thing. A cluster can run some on demands for some spots for other applications and have it all be driven by the applications themselves.